Imagine a set of ESP32 devices spread across a smart greenhouse, all needing to exchange temperature, humidity, or control signals instantly, without waiting for Wi-Fi connections. ESP Now lets them talk directly to each other, like walkie-talkies for ESP32s, using minimal energy and very low latency. In this lesson, we'll explore how to configure devices as peers, send and receive messages, and build local networks that operate reliably even without a router. You'll gain actionable skills to create real-world IoT setups where devices coordinate seamlessly, save power, and react quickly to environmental changes or user commands, enabling efficient, battery-friendly sensor networks and responsive automation systems. ESP Now is a lightweight, proprietary protocol from Espressif that enables ESP32 devices to communicate directly without connecting to Wi-Fi networks. Each device is identified by its MAC address, allowing peer-to-peer messaging in unicast or broadcast modes. Unlike standard Wi-Fi, ESP Now avoids the overhead of association and authentication, significantly reducing latency and power consumption. Messages are small, typically under 250 bytes, making it ideal for sensor readings or control signals. Think of it as a private, low-power radio channel shared by your devices. This protocol is perfect for scenarios like local mesh networks, remote control nodes, or low-power battery-operated sensors where you need reliable, immediate communication without relying on a Wi-Fi router. This table highlights why ESP Now is powerful for IoT. Low latency ensures near-instant messaging, minimal power draw extends battery life, support for multiple peers allows building small networks, and it works even if Wi-Fi is off. Each bullet represents a key advantage you can leverage in real projects. For instance, low latency is critical for automation loops, while minimal power consumption allows battery-operated nodes to last months. Multiple peer support simplifies building a mesh of devices, and working without Wi-Fi means you can deploy sensors anywhere, from farms to industrial floors, without worrying about coverage or routers. In practice, you set one ESP32 as the sender, specifying the receiver's MAC address. The code initializes ESP Now, registers a send callback, and transmits a simple message every 2 seconds. Think of this as your ESP32 calling out, "Hello," to a friend in a quiet room. If the send is successful, the callback confirms it, otherwise, it alerts you to retry. You'll see messages on the serial monitor, helping you verify communication. Configuring peers correctly and ensuring the device is in STA mode are critical steps that prevent common issues like failed transmissions or missed packets. This setup forms the foundation for more complex networks. On the receiver side, the ESP32 is set to listen for incoming ESP Now messages. The code registers a receive callback that triggers whenever a message arrives. Incoming data is captured, converted to a string, and printed on the serial monitor. Conceptually, the receiver is like a friend with ears tuned to the walkie-talkie channel, instantly catching every message. Using this callback mechanism ensures your program reacts immediately, enabling real-time data collection or control actions. Monitoring serial output confirms your network is functional and provides insights into message integrity, timing, and potential debugging needs. Once your sender and receiver are running, verify MAC addresses carefully to ensure messages reach the correct peer. Check that each device successfully registers peers and that ESP Now initialization returns ESP_OK. Always use serial monitor for real-time insights and minimize interference from other 2.4 GHz devices during testing. If messages are delayed or dropped, try moving devices closer or reducing network congestion. Testing incrementally, first with one sender and one receiver, helps isolate issues before scaling to multiple peers. These practices ensure reliable communication, help you understand ESP Now behavior, and prevent subtle bugs from impacting a larger mesh network. In the field, messages may fail due to incorrect peer configuration, wrong Wi-Fi mode, or environmental interference. If the send callback indicates failure, resetting the ESP32 or re-adding the peer usually resolves the issue. Packet loss can occur if devices are too far apart or if the 2.4 GHz band is crowded. LEDs or buzzers can provide visual confirmation when serial monitoring isn't feasible. By systematically checking these points, you ensure your network operates reliably under real-world conditions, making your ESP NOW system robust, predictable, and ready for deployment in practical IoT applications. Once comfortable with basic messaging, expand to sensor mesh networks where multiple ESP32s report temperature or humidity to a central node. You can build a handheld remote controller to actuate LEDs or relays without Wi-Fi, or combine ESP NOW with cloud uploads for hybrid systems. Battery-friendly alerts leverage deep sleep with ESP NOW wake-ups, allowing devices to transmit then sleep, saving energy. Multicast messaging broadcasts commands to several devices simultaneously, enabling synchronized actions like coordinated lighting or irrigation. Each extension reinforces practical skills in peer-to-peer communication, low-power operation, and network scaling, helping you transition from basic demos to real-world IoT systems. By completing this lesson, you've learned how ESP NOW enables direct, low-latency, and energy-efficient communication between ESP32 devices. You know how to configure peers, send and receive messages, and troubleshoot common issues. With these skills, you can design local networks without relying on Wi-Fi, build responsive sensor arrays, and create low-power automation systems. These foundations allow you to scale projects, integrate multiple nodes, and deploy IoT solutions in environments where traditional networks are unreliable or unavailable.